When people hear the phrase AI agent, they often imagine a chat window that answers questions or a robotic assistant making autonomous decisions in the background. Both ideas are close, but neither quite captures what's really happening under the hood. To understand AI agents clearly, it helps to strip away the hype and start with a precise definition. An AI agent is not a single model, and it is not just a conversation. It is a system designed to perceive information, decide what to do next, and take actions toward a goal, often repeatedly, often without constant human prompting. At its core, an agent follows a loop: observe, reason, act, observe again. This loop is what separates an agent from a simple AI response. A basic language model by itself is reactive. It waits for an input, produces an output, and stops. An agent, by contrast, is persistent. It remembers what it has already done, evaluates progress, adjusts strategy, and continues operating until a condition is met or until it is explicitly stopped. That persistence is the first key shift. In practical terms, an AI agent usually consists of several tightly connected components. A reasoning engine, often a language model, that interprets inputs and plans actions. A memory system that stores past steps, results, and context. A tool interface that allows the agent to interact with software, data, or external systems. A control loop that decides what happens next and when to stop. None of these pieces are exotic on their own. What makes an agent powerful is how they are orchestrated together. To make this concrete, imagine a simple non-agent system. You ask an AI to summarize a PDF. It reads the document and produces a summary. Done. There is no awareness of whether the summary is useful, whether key sections were missed, or whether the task should be repeated with different emphasis. Now imagine the same task handled by an agent. The agent starts by loading the PDF. It then checks the length and structure of the document, notices that it contains technical appendices, and decides to summarize the main body first. After generating a draft summary, it evaluates whether the output meets predefined criteria, say, clarity for a non-technical audience. If not, it revises the summary, possibly rereading certain sections. Only after these internal checks does it present the final result. Nothing magical happened. The agent simply decided to keep going. This idea of self-directed continuation is central. Agents are designed to manage tasks, not just responses. A task might take 1 step or 50. The agent does not need to know in advance how many steps it will take, only what success looks like. This is where goals enter the picture. An agent operates with an explicit or implicit objective, such as produce a weekly sales report using the latest database entries. Monitor system logs and flag unusual patterns. Plan and book travel under a fixed budget and schedule. The goal constrains behavior. Every observation and action is evaluated in terms of whether it moves the system closer to that goal. Without a goal, there is no agent, only a tool waiting to be used. Importantly, most AI agents are narrow and bounded, not general intelligences. They do not want anything. They do not invent goals on their own. They execute a defined loop within carefully set limits. If they appear autonomous, it is because humans have delegated decision-making within a narrow domain, not because the system has independent intent. Consider a concrete setup example at a conceptual level. Suppose you want an agent that manages customer support tickets. The agent's environment is your ticketing system. Its observations include new tickets, ticket metadata, and customer history. Its actions include drafting responses, escalating issues, or tagging tickets for follow-up. Its memory tracks which tickets it has already handled and how similar issues were resolved in the past. Its goal is to resolve tickets quickly while maintaining customer satisfaction. At no point does the agent understand customers the way a human does, but does not need to. It only needs to repeatedly evaluate, is this ticket resolved? If not, what is the best next action? This framing also clarifies what AI agents are not. They are not sentient. They are not self-improving in an unconstrained sense. They do not wake up one day and decide to pursue new ambitions. Any flexibility they show comes from design choices made upstream, how memory is handled, how tools are exposed, how goals are evaluated. In the broader AI landscape, agents represent a shift from single-turn intelligence to process intelligence. Instead of asking, "What is the best answer right now?" the system is structured to ask, "What should I do next given everything I know so far?" That question, simple on the surface, is the seed from which all modern AI agents grow. In the next segment, we'll dive into the agent loop itself in detail, how observation, reasoning, and action are formally connected, and why small design choices in that loop dramatically affect reliability, safety, and usefulness in real-world deployments. If there's a single idea that defines how AI agents work, it is the loop. Everything else, memory systems, tools, planning frameworks, even autonomy, exists to support one repeating cycle: observe, decide, act, observe again. This loop is not a metaphor. In most agent systems, it is literally implemented as a control structure that runs until a stopping condition is met. The observation step is where the agent gathers information from its environment. The environment can be almost anything: a database, a folder of documents, an API, a software interface, or even the output of its own previous actions. Observation is not passive reading, it is selective perception. The agent is usually configured to notice only what is relevant to its current goal. For example, imagine an agent designed to monitor cloud infrastructure. Its observations might include server load, error rates, latency metrics, and recent deployment logs. It does not see everything in the system, only the signals that were deliberately exposed to it. This is a crucial safety and reliability feature. An agent that can observe everything is difficult to control. An agent with scoped observations behaves predictably. Once observations are gathered, the agent enters the decision phase. This is where reasoning happens. In modern systems, this reasoning is often handled by a large language model, but the model is not reasoning in isolation. It is guided by structured prompts, system rules, and sometimes explicit planning frameworks. At this stage, the agent asks questions like, "What is the current state of the task? How far am I from a goal? What actions are available to me right now? Which action best reduces the gap between the current state and the desired outcome?" The decision phase may produce a single action or short plan consisting of multiple steps. Importantly, this plan is provisional. The agent does not assume the world will behave exactly as expected. It is prepared to revise its plan after the next observation. To see how this works in practice, consider an agent tasked with cleaning and preparing a dataset for analysis. After observing that the dataset contains missing values, inconsistent column names, and outliers, the agent might decide on a sequence: normalize column names, handle missing values, then analyze distributions. It does not commit to the entire plan irrevocably. After each step, it checks whether the data now meets quality criteria. The action phase is where the agent actually changes something, either in the external world or in its internal state. Actions can include writing files, calling APIs, querying databases, sending messages, or even prompting itself with a new internal question. In many systems, actions are executed through a tool interface that strictly defines what the agent is allowed to do. This separation between decision and action is deliberate. The reasoning engine can propose an action, but the execution layer enforces constraints. If an agent proposes an invalid or disallowed action, it is rejected before anything happens. This design prevents runaway behavior and is one of the reasons agents can be safely deployed in production environments. After an action is executed, the loop closes by returning to observation. The agent checks the result of what it just did. Did the API call succeed? Did the file update correctly? Did the system state change as expected? This feedback determines the next decision. This repeated feedback is what gives agents their apparent adaptability. They are not predicting the future in detail. They are reacting continuously to real outcomes. Stopping conditions are a subtle but critical part of the loop. An agent must know when to stop, or it will loop indefinitely. Common stopping conditions include: the goal has been met, a maximum number of steps has been reached, an error threshold has been exceeded, human intervention is required. For example, a research agent searching for academic papers might stop when it has gathered a specified number of high-quality sources, or when new searches stop yielding novel information. Without this constraint, the agent could continue searching endlessly, mistaking activity for progress. A useful way to think about the agent loop is to compare it to human problem solving. When you plan a trip, you observe constraints like dates and budget, decide on destinations, take actions like booking flights, and then recheck availability and costs. If something changes, prices spike or flights sell out, you adjust. AI agents formalize this everyday loop and execute it at machine speed. However, unlike humans, agents are only as good as their loop design. If observations are noisy, decisions will be brittle. If actions are too powerful, mistakes will be costly. If stopping rules are vague, behavior will drift. This is why real-world agent design is less about making models smarter and more about engineering the loop carefully. Small changes, such as how often the agent re-evaluates its goal or how it verifies the success of an action, can be the difference between a reliable system and an expensive failure. In the next segment, we'll focus on one of the most misunderstood parts of agent systems: memory. We'll explore how agents remember past actions, why memory is not the same as context length, and how different memory designs radically change what agent can and cannot do over time. Memory is what turns an agent from a clever loop into something that feels persistent and purposeful. Without memory, an agent would repeat itself endlessly, rediscovering the same facts and making the same mistakes. With memory, it can accumulate experience, track progress, and behave coherently across long tasks without ever understanding in the human sense. The first misconception to clear up is that agent memory is not the same thing as a model's context window. A context window is temporary. It exists only for the duration of a single reasoning step. Memory in an agent system is external, structured, and deliberately managed. It persists across steps, sessions, and sometimes days or months. Most agents use multiple types of memory, each serving a different role in the loop. The simplest form is working memory. This is short-term storage used to track the current task state, what step the agent is on, what has already been attempted, and what the next action should be. Working memory is often rewritten every cycle. It keeps the agent oriented in the present moment. For example, in a document processing agent, working memory might contain notes like sections 1 to 3 summarized, figures extracted, appendix pending. This information is not permanent, but it prevents duplication and confusion while the task is underway. Next is episodic memory, which records what the agent has done and what happened as a result. Think of this as a log of experience. Each action, observation, and outcome can be stored as an entry. Over time, this creates a traceable history of behavior. In a customer support agent, episodic memory might include ticket number 4821 escalated due to billing mismatch, resolution required human review. Later, if a similar ticket appears, the agent can recall that escalation was previously necessary. This does not require learning in the machine learning sense, just retrieval of past outcomes. Then there is semantic memory, which stores stable knowledge extracted from experience. Instead of remembering that a specific ticket was escalated, the agent might store a generalized rule. Billing disputes involving regional tax codes often require escalation. Semantic memory is usually curated, summarized, or filtered to avoid noise. This distinction matters because raw logs are not useful at scale. An agent that stores everything indiscriminately will drown in its own history. Effective memory systems deliberately compress experience into reusable knowledge. A common implementation pattern is to periodically summarize episodic memory into semantic memory. The agent might review its own logs and extract patterns, rules, or heuristics. Importantly, this summarization process is controlled and bounded. The agent is not improving itself autonomously, it is reorganizing information according to predefined rules. Memory also varies by scope. Some memories are global to the agent, while others are tied to a specific task, user, or project. A research agent might maintain long-term memory about trusted sources while keeping task-specific memory for each investigation. When the task ends, that local memory can be archived or discarded. To see how this plays out in a concrete setup, imagine an agent that manages a software backlog. Each sprint, it observes new issues, prioritizes tasks, and tracks progress. Its episodic memory logs decisions made in previous sprints. Its semantic memory captures patterns like which types of bugs tend to block releases or which modules are high risk. When a new sprint begins, the agent uses this memory to make better initial plans. Crucially, memory is not always correct. Stored information can become outdated, biased, or misleading. This is why well-designed agents include memory validation mechanisms. They may periodically recheck assumptions against fresh data or downgrade the confidence of older memories. Some systems assign decay rates so that unused memories gradually lose influence. There is also a hard boundary on what agents remember. They do not have autobiographical awareness. They do not reminisce. Memory is accessed only when it is relevant to the current decision. If a memory does not help evaluate the next action, it might as well not exist. This selective recall is intentional. Memory is expensive, computationally and operationally. Every retrieval introduces noise and complexity. Effective agent design favors useful forgetting over total recall. From a systems perspective, memory is what allows agents to operate over long horizons. Planning a multi-week project, managing a rolling dataset, or maintaining ongoing relationships would be impossible without it. But memory alone does not give an agent power. It simply gives continuity. In the next segment, we'll examine how agents interact with the outside world through tools, APIs, files, software interfaces, and why tool design is one of the most important and overlooked aspects of building reliable AI agents. An AI agent without tools is trapped in its own head. It can reason, plan, and reflect, but it cannot change anything. Tools are what connect an agent's internal decision-making loop to the external world. They are the difference between an agent that talks about work and one that does work. A tool in agent terms is any controlled interface that allows the agent to take an action beyond generating text. This can be as simple as reading a file or as powerful as deploying code to production. Importantly, tools are not discovered or invented by the agent. They are explicitly defined and exposed by humans. What an agent can do is limited by design to the tools it is given. Most tools fall into a few broad categories. The first is information access tools. These allow agents to retrieve data from databases, documents, logs, or APIs. A research agent might have tools to query academic databases, fetch web pages, or search internal knowledge bases. A business agent might pull sales numbers or customer histories. These tools expand the agent's observation space beyond what fits into a single prompt. Next are transformation tools, which let the agent modify data. This includes writing files, updating spreadsheets, editing documents, or restructuring datasets. A reporting agent might fetch raw metrics, clean them, generate charts, and write a final report, all through transformation tools. Then there are action tools which affect external systems. These include sending emails, creating tickets, triggering workflows, or executing scripts. These tools are where agents become operationally useful and where risk increases sharply if boundaries are not well defined. To understand why tool design matters so much, consider a simple example: an agent tasked with managing calendar scheduling. If the agent has a single tool called Update Calendar, it may attempt broad changes with limited oversight. If instead it has narrowly scoped tools, check availability, propose meeting time, create draft event, each action becomes safer and more interpretable. Well-designed tools are explicit, narrow, and reversible. Each tool has a clear purpose, strict input and output formats, well-defined permissions, predictable side effects. This structure allows the agent to reason about tools symbolically. It does not need to understand how an API works internally. It only needs to know what the tool does, what inputs it accepts, and what outcomes to expect. Let's look at a concrete setup example. Imagine an agent designed to generate weekly business reports. It might be given the following tools: fetch_metrics, start_date, end_8, clean_data, dataset, generate_summary, cleaned_data, write_report, summary, destination. Each tool does one thing. The agent's reasoning step decides which tool to call and in what order. After each call, the result is observed and evaluated. If clean_data fails due to missing fields, the agent can decide to fetch additional metrics or adjust parameters. Notice what the agent is not doing. Is not writing raw SQL. Is not manually formatting files. Those details are hidden behind the tools. This abstraction is intentional. It keeps reasoning and execution decoupled. Tool access also introduces the need for tool choice discipline. Agents should not call tools just in case. Each tool call has cost, latency, and risk. Poorly designed agents overuse tools, treating them as exploratory probes rather than deliberate actions. Good agents treat tools as commitments. Another subtle point is that tools are part of the agent's environment. Tool outputs become new observations, feeding back into the loop. If a tool returns unexpected results, the agent must decide whether to retry, escalate, or change strategy. This is why robust error handling is critical. Tools should return structured errors that the agent can reason about, not vague failure messages. In production systems, tools are often wrapped with additional safeguards. Rate limits, approval gates, dry run modes, and logging layers are common. These do not make agents less capable, they make them trustworthy. A powerful agent that cannot be audited is a liability. There's also a strategic choice in whether tools are synchronous or asynchronous. Some actions, like database queries, return immediately. Others, like long-running analyses or external approvals, may take time. Agents must be designed to handle waiting states without losing context or repeating actions unnecessarily. From a broader perspective, tools define the agency surface. They are the levers an agent can pull. Expanding that surface increases capability, but also complexity. Most successful deployments start with very limited tools and expand cautiously as behavior becomes well understood. In the next segment, we'll explore how agents plan across multiple steps, how they break large goals into sub-goals, revise plans when things go wrong, and avoid the common failure modes that plague long-horizon reasoning. Planning is where AI agents start to feel intelligent, not because they foresee the future, but because they structure uncertainty. A plan is not a promise, is a working hypothesis about how to move from the current state to a desired outcome. Good agents plan lightly, revise often, and never confuse a plan with reality. At a technical level, planning is the process of decomposing a goal into intermediate states that can be reached through available actions. The agent asks a simple but powerful question: what would the world look like if I were closer to success? Then it works backward or forward to identify steps that might produce that state. Most modern agents do not generate one rigid plan at the beginning and follow it blindly. Instead, they engage in incremental planning. After each action, they reassess whether the plan still makes sense given new information. This is one of the main advantages agents have over traditional scripted automation. There are several common planning styles used in agent systems. The simplest is linear task decomposition. The agent breaks a goal into a sequence of steps and executes them in order. For example, an agent tasked with producing a market analysis might plan, collect data, clean data, analyze trends, write summary. This works well when the task is well understood and the environment is stable. More advanced agents use hierarchical planning. Here, the agent defines high-level subgoals and delegates details to lower-level plans. A travel planning agent, for instance, might define subgoals like transport, lodging, and activities, then plan each independently. If one subgoal fails, say no flights are available, the agent can revise that branch without discarding the entire plan. Some agents employ reactive planning, where planning and execution are tightly interwoven. Instead of committing to future steps, the agent chooses the next best action based on the current state and replans continuously. This approach is robust in noisy or unpredictable environments, but can be inefficient if not bounded. To see planning in action, consider a concrete setup, an agent tasked with migrating a legacy dataset to a new schema. The goal is clear, but the path is not. The agent begins by inspecting the existing data, identifies incompatible fields, plans a mapping strategy, and tests a small subset. If errors appear, it revises the mapping before scaling up. Planning here is exploratory, not prescriptive. One of the hardest problems in agent planning is overconfidence. Language models are good at producing plausible plans, even when those plans are flawed. Without feedback loops, an agent might confidently pursue a path that leads nowhere. This is why planning must be grounded in verification. After each step, the agent checks whether reality matches expectation. Another common failure mode is overplanning. Agents can waste time generating elaborate plans for simple tasks. To counter this, many systems impose planning budgets, limits on how many steps or tokens can be spent planning before acting. This forces the agent to balance thinking and doing. Planning also interacts closely with memory. Past failures inform future plans. If an agent remembers that a certain approach consistently fails, it can avoid repeating it. This does not require learning in the traditional sense, just retrieval and comparison. There is also an important distinction between open-ended goals and closed-ended goals. Closed-ended goals, like generate a report, have clear completion criteria. Open-ended goals, like monitor system health, require ongoing planning with no natural endpoint. Agents handling open-ended goals must rely heavily on stopping conditions and prioritization rules to avoid drift. From an engineering standpoint, planning is less about intelligence and more about control. A well-designed planning system makes agent behavior interpretable. You can inspect why the agent chose a certain path, what alternatives it considered, and where it changed course. This transparency is essential for debugging and trust. In the next segment, we'll examine how multiple agents can work together, how responsibilities are divided, how agents communicate, and why multi-agent systems introduce both powerful capabilities and entirely new classes of failure. A single AI agent can handle many tasks, but complexity grows quickly. As goals become broader or more parallel, designers often split responsibilities across multiple agents. This is not about making the system smarter. It is about managing scope, reducing cognitive load, and improving reliability through specialization. A multi-agent system is exactly what it sounds like: multiple agents, each with its own loop, memory, and tools, coordinated to achieve a shared or overlapping set of goals. Each agent is still narrow and bounded. The intelligence emerges from how they interact. The simplest multi-agent setup uses role separation. Each agent is assigned a distinct responsibility. For example, in a research pipeline, you might have a retrieval agent that gathers sources, an analysis agent that evaluates credibility and extracts insights, a writing agent that synthesizes findings into prose. Each agent operates independently but passes outputs to the next stage. This approach mirrors how human teams work and makes systems easier to reason about. More advanced systems use collaborative agents, where agents can request help from one another or critique each other's outputs. One agent might propose a solution, while another checks it for errors or bias. This reduces overconfidence and catches mistakes that a single agent might miss. Consider a concrete example: an agent system managing a software release. One agent monitors test results, another reviews documentation, and a third evaluates deployment readiness. If the testing agent detects failures, it signals the coordinator agent, which delays release and requests further analysis. No single agent has full authority, but together they enforce quality. Communication between agents is usually structured and limited. Agents do not chat freely. They exchange summaries, flags, or task updates through defined channels. This prevents feedback loops where agents amplify each other's errors. However, multi-agent systems introduce new failure modes. Agents can disagree, deadlock, or pass responsibility endlessly. Without clear coordination rules, systems can stall or behave unpredictably. This is why many designs include a supervisor agent or orchestration layer that assigns tasks, resolves conflicts, and enforces stopping conditions. Another challenge is memory consistency. Each agent may have its own memory, but shared context must be synchronized carefully. If agents operate on outdated or conflicting information, coordination breaks down. In practice, shared memory is often read-only, with updates gated through a central authority. Multi-agent systems are powerful when tasks are naturally decomposable and parallelizable. They are overkill for simple workflows. Adding agents increases overhead, latency, and debugging complexity. Good designs start with one agent and scale outward only when bottlenecks become clear. From a philosophical perspective, multi-agent systems highlight an important truth. Intelligence is often less about raw capability and more about organization. Dividing problems into manageable roles makes complex behavior tractable. In the next segment, we'll explore how agents are constrained and controlled, guardrails, permissions, evaluation metrics, and human-in-the-loop designs that prevent agents from doing the wrong thing, even when they appear to be working. The most successful AI agents are not impressive. They are boring, predictable, and uneventful. That is not a failure of ambition. It is the result of good control design. Guardrails are what keep agents aligned with their intended purpose and prevent small errors from becoming expensive problems. At a technical level, guardrails are constraints applied at every layer of the agent loop. What the agent can observe, how it can reason, which actions it can take, and when it must stop. An agent without guardrails is not autonomous, it is reckless. The first layer of control is scope limitation. Agents are given access only to the information and tools they absolutely need. If an agent does not need to modify production systems, it should not have write access. If it does not need user-identifying data, that data should be invisible. This principle dramatically reduces risk without reducing usefulness. Next are action constraints. Tools are often wrapped with validation logic that checks inputs and enforces policies. For example, an agent drafting customer emails might be prohibited from sending messages without human approval or from contacting users outside business hours. The agent can propose actions, but the system decides whether they are allowed. Another critical guardrail is rate and budget control. Agents that call APIs, run computations, or generate outputs must operate within defined limits. Without these limits, agents can spiral into costly loops, mistaking activity for progress. Budget constraints force agents to prioritize and to stop when diminishing returns appear. Evaluation is also a form of control. Agents can be required to self-check their outputs against predefined criteria before acting. A data analysis agent might verify statistical validity. A writing agent might check for clarity or policy compliance. These checks do not guarantee correctness, but they reduce obvious failures. Human-in-the-loop designs are especially important for high-impact decisions. In these systems, agents prepare recommendations, drafts, or plans, but humans approve or reject final actions. This keeps responsibility clear and allows agents to operate as accelerators rather than decision-makers. Logging and observability are often overlooked but essential. Every observation, decision, and action should be traceable. When something goes wrong, engineers need to know not just what happened, but why. Good logs turn agent behavior into something that can be audited and improved. A subtle but powerful guardrail is task framing. How a goal is defined determines how an agent behaves. Vague goals invite drift. Precise success criteria produce focused behavior. Improve customer satisfaction is an invitation to chaos. Reduce average response time by 10% without increasing escalations is something an agent can reason about. Importantly, guardrails do not eliminate flexibility, they shape it. Within a well-defined boundary, agents can explore, adapt, and recover from errors. Outside that boundary, they simply cannot act. In the next segment, we'll look at how agents are evaluated over time, how success is measured, how failures are diagnosed, and how systems improve without turning into opaque, self-modifying black boxes. Once an agent is deployed, the most dangerous assumption you can make is that it will continue behaving well on its own. Agents do not slowly improve through experience unless you explicitly design them to. Without evaluation and feedback, they can silently degrade, drift off goal, or fail in subtle ways that are hard to notice until damage is done. Evaluation answers a simple question: is the agent doing what it was designed to do? But in practice, that question splits into many smaller ones, each requiring a different kind of measurement. The first distinction to make is between task success and system health. Task success asks whether the agent completed its objective. System health asks whether it did so efficiently, safely, and consistently. An agent that technically completes tasks but burns excessive resources or requires constant human cleanup is not successful. For closed-ended tasks, evaluation can be straightforward. Did the report generate correctly? Were all required fields filled? Did the deployment complete without errors? These outcomes can be measured automatically and logged. For open-ended or qualitative tasks, evaluation is more nuanced. Consider an agent that drafts internal documentation. The output may be grammatically correct and factually accurate, but still unhelpful. In these cases, evaluation often combines automated checks with human review. Metrics might include readability scores, revision rates, or user feedback over time. A common pattern is step-level evaluation, where the agent evaluates its own intermediate actions. After each tool call or major decision, the agent checks whether the result aligns with expectations. If not, it flags a step for review or retries with a different approach. This kind of self-evaluation catches failures early before they compound. Another important concept is baseline comparison. Agents should not be evaluated in isolation. Their performance should be compared to simpler alternatives, scripted automation, human workflows, or even doing nothing. If an agent is slower, more expensive, or less reliable than a baseline, its sophistication is irrelevant. Feedback loops are how evaluation informs improvement, but this is where discipline is required. Improvement does not mean letting the agent rewrite its own rules. Instead, humans analyze logs, identify failure patterns, and adjust prompts, tools, memory policies, or constraints. The agent remains stable. The system around it evolves. This separation prevents the system from becoming an opaque black box. The agent does not mutate unpredictably. Changes are intentional, documented, and reversible. There is also a temporal dimension to evaluation. Some failures appear immediately. Others only emerge after weeks of operation. Agents that interact with changing environments, markets, user behavior, data streams, must be periodically re-evaluated against current conditions. Assumptions that were valid at deployment may no longer hold. One subtle failure mode is silent success. An agent may appear to be working because it produces outputs, but those outputs are ignored or unused. Logs look clean, but value is not being created. Effective evaluation looks beyond execution and measures impact. In mature systems, evaluation results feed into alerting and governance processes. If an agent's performance degrades beyond a threshold, it may automatically switch to a safe mode, reduce its autonomy, or require human approval for actions. This ensures that failures degrade gracefully rather than catastrophically. Ultimately, evaluation is what keeps agents grounded in reality. It replaces assumptions with evidence and enthusiasm with accountability. In the next segment, we'll explore how agents are actually set up in practice, from simple single-agent scripts to production-grade architectures, and what trade-offs engineers face when moving from experimentation to real-world deployment. The gap between a demo agent and a production agent is wide. Prototypes are forgiving. Production systems are not. The transition from "this works on my machine" to "this runs reliably every day" is where most agent projects succeed or fail. In early prototypes, an agent is often little more than a loop wrapped around a language model with a few tools. Prompts are loose, memory is minimal, and failures are tolerated. This phase is valuable. It reveals what the agent could do. But production work is about defining what the agent must not do. A typical production-grade agent setup has several distinct layers. At the center is the agent core, the reasoning loop, memory access, and decision logic. This layer is deliberately simple. Complexity here makes behavior unpredictable and difficult to debug. Many production systems limit the agent to short planning horizons and explicit step budgets. Surrounding the core is the tooling layer. Tools are implemented as hardened services, not ad hoc scripts. Inputs are validated, outputs are structured, and failures are explicit. Tools are versioned so behavior does not change unexpectedly when underlying systems evolve. Next comes the orchestration layer, which manages execution. This includes scheduling retries, timeouts, and concurrency control. The agent does not decide when to run or how often. It is invoked under controlled conditions, often as part of a larger workflow. Memory in production is carefully engineered. Short-term memory may live in fast storage for quick access. Long-term memory may be stored in databases or vector indexes with strict retrieval rules. Importantly, memory writes are often gated or reviewed to prevent the accumulation of low-quality or misleading information. Security and compliance wrap the entire system. Agents authenticate like any other service. Their actions are logged, monitored, and auditable. Sensitive data is masked or excluded entirely. In regulated environments, agents may operate in read-only modes until explicitly promoted. A concrete example helps illustrate this. Imagine deploying an agent to assist with financial reconciliation. In prototype form, it might freely query transaction data, generate adjustments, and suggest corrections. In production, that same agent would read from sanitized data views, generate reconciliation proposals rather than applying changes, require human approval before any write operation, log every recommendation and its rationale. The agent's intelligence did not change. The system around it did. Another major trade-off is latency versus reliability. Fast agents make more mistakes. Slower agents that validate each step are safer but less responsive. Production systems often expose both modes, a fast draft mode for exploration and a slow, verified mode for execution. Versioning is also critical. Agent prompts, tool definitions, and memory schemas change over time. Without version control, behavior becomes impossible to reproduce. Mature teams treat agent configurations like code, reviewed, tested, and rolled out gradually. Testing agents is its own challenge. Traditional unit tests are insufficient. Instead, teams use scenario-based tests, known situations with expected behaviors. If an agent's response to a scenario changes unexpectedly after an update, that update is flagged. The most important mindset shift is this: production agents are infrastructure, not experiments. They must fail gracefully, explain themselves, and stay within bounds, even when conditions change. In the final segment, we'll step back and look at what AI agents are for, where they deliver real value today, where they are overhyped, and how to think clearly about their role in future systems without drifting into science fiction. After all the mechanics, loops, memory, tools, planning, guardrails, the final question is the simplest and the hardest. What are AI agents actually good for? The answer is more restrained than marketing suggests, but more interesting than science fiction. Agents excel at structured, repeatable decision work that sits between pure automation and fully human judgment. They are most valuable in domains where tasks are too variable for rigid scripts, but too constrained to justify constant human attention. In other words, agents thrive in the middle ground. A strong real-world use case is workflow coordination. Agents can manage processes that involve multiple steps, systems, and checks, preparing reports, reconciling data, triaging requests, monitoring infrastructure, or maintaining documentation. These tasks are not intellectually profound, but they are cognitively expensive over time. Agents reduce friction rather than replace insight. Another clear win is information synthesis over long horizons. Research agents that gather sources, track evolving topics, and maintain living summaries are genuinely useful. Their value does not come from brilliance, but from persistence. Humans get tired, agents do not. As long as evaluation and scope are tight, this persistence compounds. Agents also shine as interfaces between systems that were never designed to work together. When APIs are inconsistent, documentation is incomplete, or data formats drift, agents can adapt dynamically in ways brittle automation cannot. This makes them powerful glue in messy, real-world environments. Where agents struggle is in open-ended, high-stakes judgment. They do not understand consequences in a human sense. They optimize toward defined objectives, even when those objectives are poorly chosen. If the goal is misaligned, the agent will pursue it faithfully and incorrectly. This is not malice, it is design. This is where hype tends to break. Agents are not general workers. They do not replace teams. They do not run companies. Every successful deployment involves humans defining goals, reviewing outputs, adjusting constraints, and deciding what matters. The agent is an amplifier, not an originator. There's also a tendency to over-attribute intelligence to coordination. When multiple agents interact smoothly, the system can look eerily competent. But beneath the surface, each agent is still executing narrow loops with bounded tools. The appearance of agency emerges from orchestration, not consciousness. Looking forward, the most meaningful progress will not come from making agents more autonomous, but from making them more legible. Systems that can explain why they acted, what alternatives they considered, and where uncertainty remains will be trusted and adopted. Systems that hide complexity behind confident outputs will not. In the InSlowSpective sense, AI agents represent a quiet shift. Not a leap toward artificial minds, but a reconfiguration of work. Decision-making becomes more modular. Attention becomes a scarce resource that machines help preserve. The question is not whether agents will act on our behalf, they already do, but how carefully we choose the boundaries within which they operate. In the end, the future of AI agents is not about surrendering control. It is about designing systems that know exactly how much control they have and stop there.